Hi everyone, welcome back to my channel Maths with Smart Tips. Today in this video, I am start to solve the WBSET 2020 Mathematical Science question paper, and this is the question booklet series X. There are total 100 MCQ questions in this paper. This is paper 2 and I am trying to solve most of the problems from these 100 problems. So let's try to solve the problems, and before starting the video, I am requesting you to all those who are new in my channel, please like the video, comment if you have any doubt in the comment section below, and subscribe the channel. So let's start to solve. Let G be a commutative group of order 202, then the number of elements of order 2 in G is. Now we have a concept. The concept number 1 which is used here is, if P is a odd prime, then any group of order 2p is either cyclic or dihedral. Now it is given that it is a commutative group, and since dihedral group for n greater equal to 3 is not commutative group, so the group of order 202 must be cyclic. And it is also noted that 202 equal to 2 into 101, which is of the form 2p, and 101 is equal to p, which is an odd prime. So here we use another concept, which is concept number 2 is used here. Number of cyclic subgroup of order D in G is equal to number of elements of order 2 in G. Since here we have to find the number of elements of order 2 in G by the general concept is of order D in G by phi of D. Now we also know that the number of cyclic subgroups of any order in this group is unique, of any cyclic group is unique. Therefore the number of cyclic subgroup of order D in G, here it is of D. Therefore the number of cyclic subgroup of order 2 is unique, which is equal to 1, is equal to number of groups of order D in G. We have to find this number of elements of order 2. Therefore number of elements of order 2 by phi of 2. Therefore this implies number of elements of order 2 is equal to 1 into phi 2. This is Euler's phi function, and we know that the value of phi 2 is 1, so this gives 1. Therefore the correct answer is 1 here. Now we go to the next question, question number 2. The question number 2 says that in a group of all invertible 4x4 matrices with entries in the field of 3 elements, then any silo 3 subgroups has cardinality. Now there is the important key terms, which is given that the matrix 4x4 matrix are of all invertible. Therefore this is clearly says that the group is the general linear group. The general linear group GLN FQ. This is the field with Q elements, or this is the field with, you can say, P elements. So this is the general linear group of, this is the order of the matrix here 4, and this is the field with P elements. So here the value of n equal to 3, and the value of n in the order of the matrix is equal to 4, and the value of P is equal to 3. Now we have a result, number of PSSG, that is silo subgroup, P silo subgroup in GL NFP is equal to p to the power n into n minus 1 by 2. Therefore here we have the value of p and n, so this is equal to 3 to the power n means 4 into 4 minus 1 by 2. So this is equal to 4 to the 2, 3 to the power 6, and which is equal to 729. Therefore the correct answer is 729, which is option D. Now question number 3. The question number 3 says that the zeros of the function fz equal to this. We have to find the zeros of this. Now we have to find the zeros such that fz equal to 0. So this implies sine of 1 by 1 minus z equal to 0, and this is equal to sine n pi, the general solution of this sine n pi. Therefore we have 1 by 1 minus z, this is equal to n pi, where n belongs to z, 0 plus minus 1 and plus minus 2, and this is equal to 1 minus z equal to 1 by n pi. Now this is not exist if we take n equal to 0. Therefore we take the value n equal to plus minus 1, plus minus 2, and so on. Now this is equal to, this implies z equal to 1 minus 1 by n pi, where n equal to plus minus 1, plus minus 2, and so on. Therefore the zeros of the given function is this 1 minus 1 by n pi. So option C is the correct answer here. Now we go to the fourth question. The question number 4 is an complex integration, which is comes from complex analysis. Now the value of the integral dz by z into z plus pi iota, where c is the in circle or mod of z plus 3 iota is equal to 1, that is radius 1 and center at minus 3 iota. Now we first draw the region, this circle. So this is 0 0, minus iota, minus 2 iota, minus 3 iota, and minus 4 iota. So the radius of the circle is 1 and the center is minus 3 iota, because this is the general form is mod of z minus z0 equal to r. This is the general form. So this is 3 iota, and we draw the circle like this. Now iota, 2 iota, this is 3 iota, and 0, this is the center of the circle. Now the singularities of the functions comes from z into z plus iota pi is equal to 0. Therefore either z equal to 0 or z equal to minus I pi, minus iota pi. Now we have to check which points lies this inside the circle. It is noted that z equal to 0, that means origin, does not lie inside the circle, and z equal to minus I minus iota pi, which is inside the circle. Since the value of pi is nearly equal to 3.14, which is lies inside the circle. Since this is the point minus 4 iota and 0 minus 4 iota, 0 minus 4 iota, the center is 0 and minus 3 iota, 0 and minus 3 iota. Therefore this lies suppose here. Therefore this is the inside the circle, this is inside the circle. Now by Cauchy residue theorem we have find this value of the integral. Use Cauchy theorem of integration. We have the value of the integration fz by integral over c z minus z0 equal to simple form 2 pi iota into f of z0 if z0 is the singularity. So we use this formula here. So here z0 means here we take fz equal to 1 by z. So we write the functions as 1 by z into z plus iota pi. This is the point of singularity, so we write it as 1 by z plus iota pi. We take this function as fz, so fz equal to 1 by z. Therefore, using this theorem, Cauchy, we have into the value of the integral dz by over c z into z plus iota pi iota is equal to 2 pi I into f at the point minus iota pi. So this is equal to 2 pi iota into 1 by minus iota pi. So iota pi cancel, so this gives minus 2 is the correct answer, but there is no option included this 2 minus pi, so I think the options should be wrong here in this question. So we go to the next question, question number 5. And one more important thing, that if this video is helpful for you, then please give a like to this video and subscribe the channel, and mustly share with your friends. So question number 5 says that a non-constant entire function, option A has at least one zero in C, option B cannot have infinite number of real zeros, option C cannot have countable number of zeros in a bounded region of C, option D cannot have an uncountable number of zeros in C. This question is also from complex analysis, so we have to solve this problem by discarding the option. So option A says that A has at least one zero in C and f is a non-constant entire function. I take fz as exponential z, that is e to the power z. We know that this is a non-constant entire function, but this function have no zeros in C. Therefore, option A is wrong here. Now we go to the question number options B. It cannot have finite number of real zeros. Suppose we take sin z. Now sin z equal to 0 implies sin n pi. So this implies z equal to n pi, and this is equal to n pi. Z equal to z means x plus iota y, so this gives x equal to n pi. And if we take any region, then it should be, it has countable number of zeros, which you can say finite. Therefore we can discarded option B also. Also, if you can take z equal to 0 here, z, you can take fz equal to z, so this is also gives finite number of zeros, that is z equal to 0. You can take this example also for discarding the options. Can you take cannot have finite number of real zeros, but this function has finite number of zeros. Real zeros means the real x, since z equal to x plus iota y, so this x part gives the zeros. If you can take 0, then I can write 0 plus iota into 0. You can take this example also for discarding B option. The option C says that cannot have countable number of zeros in a bounded region of C. Now I take an example, fz equal to exponential z minus 1. This is also a non-constant entire function. Now we find the number of zeros. This gives on a bounded region. Suppose I take the region mod z r equal to mod z less equal to, I take 7 or 8, I adjust later, since this is an bounded region, bounded circle, so it is bounded. Now I can take fz equal to this, so fz equal to 0 gives e to the power z minus 1 equal to 0. This gives, the general solution is e to the power z equal to 1 equal to e to the power 2n pi iota. So this gives z equal to 2n pi iota. Now in the region mod z equal to 8, that is a circle of radius 8. Suppose this is the circle of radius 8. Now if we put the value n equal to 1, then we get z equal to, for n equal to 1, z equal to 2 pi iota, which is nearly equal to, if we take the values nearly equal to 3, then this is nearly equal to 6 iota, which is inside the circle. Since this is a radius 8, so 6 lies suppose here, 6 iota. And also if we take the value of minus 1, n equal to, then we get minus 6 iota, which is here minus 6 iota. Therefore we get the finite number of zeros in a bounded region inside C. Therefore this option is also discarded, and the fourth option is simply true here. So cannot have uncountable number of zeros. Also you can say a result, a non-constant entire function can at most countable number of zeros. Since if there is an uncountable number of zeros, then suppose fz1 and so on equal to 0, fz1 equal to fz2 equal to 0, uncountable number of zeros, then the zeros are z1, z2 and so on. And if the limit points of these z1, z2 and so on is also lies in throughout the C, then by identity theorem you can say fz is identically 0. Therefore the zeros of the identity the zeros of a function, non-constant entire function, cannot have uncountable number of zeros. Therefore zeros of the non-constant entire function is at most countable. So this is the question. And question number 6, which is also comes from complex analysis. The question 6 says that A, the points complex number z such that which satisfies this condition. It is a simple question if we solve this in a simple way. So how can we solve this? The question says that z mods of z minus 2 plus mod of z minus 1 greater or equal to 3 greater or equal to 3, z belongs to C. Now we put any value of z. It is noted that if we put any value of z, any point, suppose we take iota, z equal to iota, simply I take. So find the mod of z minus 2 plus mod of z plus 1, which is equal to iota, since iota minus 2 plus iota plus 1. This gives root under of x plus iota y, so minus 2 whole square plus 1 square plus root under 1 square plus 1 square, and this is equal to root under 5 plus root under 2, which is strictly greater than equal to 3, you can say. And if we put any complex number z here, suppose you can take 1 plus iota 0, you can take z equal to 1. This is an also complex number if you put here. So 1 minus 2 plus 1 plus 1. So this is 1 and this is all 2 gives greater or equal to 6. This satisfied. Therefore the A is, if we take any complex number, so any complex number satisfies this condition. So the simple answer is A equal to C here. This is the complete complex plane. Simple trick. The next question is question number 7, which is also comes from complex analysis, complex integration. Now the value of the integration mod z equal to 1 to a cos of exponential z by z into dz. Now in mod z equal to 1, the only singularity is z equal to 0, which is lies inside the this mod z equal to 1. Therefore by Cauchy residue theorem from stated above, we take fz equal to cos of e to the power z here. Therefore by Cauchy theorem, the value of the integration over C, that is mod z equal to 1, fz by z, take fz here, which is dz equal to 2 pi iota f of singularity at the point is 0. Since 0 is the singularity, so this is equal to 2 pi iota f0 means cos of 0. This gives 2 pi iota into cos of 1. Now we write the cos theta as exponential iota theta plus exponential minus iota theta by 2. We use it here. So this gives 2 pi iota into exponential iota plus exponential minus iota by 2 as theta equal to 1 here. So 2 say 2 cancel, and this gives pi iota into exponential I plus exponential minus I, which gives the correct answer, option D. Now go to the next question. The total number of zeros of the function fz equal to z to the power 4 minus 5z plus 1 within this annulus region. Now we first draw a circle. The circle, this is a circle, and suppose we take another circle. The circles are like this. This is the two circles, and I write also the axis also. These are the axes I can take. Now we have to find the zeros. First, mod z equal to 1. Suppose this is the circle with radius r equal to 1, and the circle, this is the radius r equal to 2. We have to find the zeros between 1 less than mod z less than 1. That is, how many zeros in this region we have to find. So we use Cauchy theorem here. First we have find the zeros between this small circle, that is the circle with radius 1, and then find the zeros inside the circle mod which is of radius 2, that is total, and then subtract these 2, then we get our required result. Now we first find the zeros between mod z less than 1 or less equal to 1, you can take. So Cauchy's theorem says that we use here Cauchy's theorem. Cauchy's theorem says that if fz and zz are two analytic functions inside and on a simple closed curve C, and if mod of zz less than equal to mod of fz, then fz and fz plus zz has same number of zeros. So here the function is fz, so I can take fz equal to, I write zz plus hz. Now if fz, I use these two functions for Cauchy theorem. So if I first erase this. Now if zz and hz are two analytic functions inside and on a simply closed curve, then gz and gz plus hz have same number of zeros inside this region C. This is the Cauchy's theorem. Now first we take mod z equal to 1, we have to choose the function gz and hz. Now we choose fz equal to given z to the power 4 minus 5z plus 1, z to the power 4 minus 5z plus 1, this. Now we choose hz for mod z less equal to 1. Choose hz equal to minus 5z. In this region we choose hz, which is the numerically largest coefficient, and the power of z is minimum. So this is the numerically largest coefficient, and gz equal to the remaining term z to the power 4 plus 1. Now at mod z less equal to 1, mod of gz, at mod z equal to 1, mod of gz equal to, put 1 here, maximum value is equal to 2, which is less equal to mod of hz, which is equal to 5z equal to 5. So the zeros of hz and gz plus hz are same. Now we put hz equal to 0, this gives minus 5z equal to 0, and this gives z equal to 0. Therefore 1 0 lies between the circle this mod z equal to 1. Now we find the number of zeros in mod z. I use this color, mod z less equal to 2. So for this region we take hz equal to this z to the power 4 plus 1 and gz equal to minus 5z. For this region we choose fz and gz such a way such that gz is less equal to mod gz less equal to mod of hz. Now mod of gz equal to mod of gz equal to 5 into 2 on the boundary, so this gives 10, and mod of hz, this is equal to 2 to the power 4 plus 1, this equal to, suppose, which is greater than 10, you can say 2 to the 4 to the 8 to the 16 1 1 17. So mod of gz less equal to mod of hz here. This, therefore we can apply Cauchy's theorem, which says that gz and gz plus hz have same number of zeros. Now we put hz equal to 0, which gives hz, we choose here hz equal to, sorry, this is the z to the power 4 only, sorry, I made a mistake here. hz mod gz equal to 2 to the power hz equal to 5z plus 1, which gives z equal to 11, this gives 11, and 2 to the power 4 equal to 16. So mod of hz equal to 0 gives z to the power 4 equal to 0, which is the number of zeros equal to 4. Therefore the region, in this region, in the circle of radius 2, the total number of zeros will be 4, and in the circle with radius 1, inside this circle small is 1. Therefore total zeros in this region is equal to 4 minus 1 is equal to 3, which we have to find. So this correct answer is 3 here. Now we go to the next question, question number 9, which is also comes from complex analysis. Question number 9 says that summation z power n, which of the following statement is not true? This not term is very important, because in the examination we forget this term. Now option A says that sum z to the power n plus sum z to the power n by n square have same radius of convergence. Now the radius of convergence, if r is the radius of convergence, then we find 1 by r equal to limit n tends to infinity n plus 1 by n, where the power series is summation n z power n. So for the first series summation z power n, here n equal to 1, so 1 by n plus 1 equal to also 1, and if we put here, so we get simply r equal to 1 here. So the first series is remaining, first series the radius of convergence is 1. Now in the second series summation z to the power n by n square, here a n equal to 1 by n square, so a n plus 1 equal to 1 by n plus 1 whole square, and this gives a n plus 1 by n equal to n square by n plus 1 whole square, which tends to 1 as n tends to infinity. This is the limit. Therefore here also r equal to 1. Therefore this is correct option, and here we have to find not correct option, so this is false option. Now z to the power n converges nowhere on the boundary of the disk of convergence, that is here the interval of convergence is minus r and r, so this is equal to minus 1 1 1, and we have to find the convergence at z equal to 1 and minus 1. Now we put the value in the series summation z to the power n. Now summation z to the power n means 1 to the power n, which is an infinite series, which is not convergent series. This series is not convergent. Also summation minus 1 to the power n, this series is also is not convergent. Therefore the convergent nowhere on the boundary, so it is the correct option, it is true option, therefore it is not correct. Now option number D says that converges everywhere on the boundary of its disk of convergence. We check it that the series z to the power n is not convergent at the boundary of the disk of convergence, therefore this is the wrong option, so it is the correct option. This is not true and we have to find not true option, so this is the correct option. Also you can check this, but I think we don't need to check it. So this is the video, and how was the video? If the video is helpful, then please give a like to this video. If you have any doubt and any other comment, so please do comment in the comment section, and thank you friends, thank you for watching.